Structural batteries combine electric energy storage with load-bearing capabilities. This technology promises to reduce the weight of batteries and opens up new possibilities for distributed electric energy storage on board future aircraft. In the MATISSE project, we are developing structural batteries and multifunctional composite energy storage for aeronautic applications. We are also making the battery smart by integrating microelectronics to monitor the health of the battery and the structure in which it is embedded. Finally, we will demonstrate our technology in a novel wingtip for an all-electric light sport aircraft, the Pipistrel Willys Electra.
AIT, together with KIT and Sensor Chips, is responsible for developing and producing the smart structural battery cells in MATISSE. We have developed a structural battery system using a semi-solid electrolyte, which maintains its electrochemical performance while at the same time can bear significant amounts of load. In addition, the developed system shows a high level of safety, is non-flammable and non-toxic. This means that the assembled cells can be handled under ambient conditions for integration purposes. Finally, scalability studies show that all components, the electrodes and the electrolyte, can be processed using traditional battery production technologies and thus are in line with industrial requirements.
The CMU-I has been designed as a tiny, single flexible circuit that on one side features sensors and a Sensi Plus microchip, and on the other side a copper plate that doubles as the anode of the smart battery cell. When integrated in the stack of a lithium-ion pouch assembly, the CMU-I replaces the anode foil, while adding all its sensing capability. The CMU-I allows performing multiple state and structural measurements of batteries inside the application and while it is in operation. For structural integrity monitoring, the Sensi Plus chip measures two interdigit electrodes with X and Y orientation to capture multiple structural events such as bending, torsion, pressure, impact, and formation of cracks, delamination, or accumulation of moisture.
The study of mechanical response of aeronautical components under dynamic impact loading condition at a low impact energy level is a very important issue in the design of composite structure. Also, structural batteries are very insensitive to this type of damage, commonly referred as a BIT. In MATISSE project, CIRE is involved in the development of numerical tools based on finite element code, able to predict the possible onset and propagation of such kind of damages with a reasonable accuracy.
The design of next-generation electric and hybrid electric aircraft can be significantly enhanced by integrating health monitoring systems into new multifunctional structures. One of the added value within the scope of MATISSE project is the realization of a real-time integrated SHL system by integrated self-powered digital microelectronics, cost-effective power supply, and data cables, enabling continuous battery functionality checks.
In Pipistrel, we are manufacturing the MATISSE wingtip demonstrator at our production facilities. The wingtip is fully made of carbon fiber composite and is embedding 40 battery cells inside the sandwich composite skin. This represents a big challenge because it's the first time ever that this technology is applied to an actual complex aeronautical assembly. We focus on analyzing how much we can reduce the weight and increase endurance using structural batteries instead of conventional battery packs. This comparison is allowing us to benchmark the estimation of the technology made at the beginning of the project. Demonstrating our expectations with results on a complete aircraft will show more realistically and clearly the strengths and opportunities of the smart structural batteries for aeronautical applications.
Onera is in charge of the design and execution of a test campaign to characterize the mechanical properties of a sandwich composite made of a recently developed high-performance out-of-plane laminated carbon epoxy material combined with a foam. Pipistrel has provided a promising geometry of an innovative wingtip into which battery cells can be integrated in an efficient and robust manner in order to validate the design in terms of strength analysis and local buckling. The objective of such a structural simulation is firstly to assist in the design of the material test campaign to ensure that the required material properties are measured in preparation for the final test. Secondly, to optimize the final test of the demonstrator to generate boundary conditions that are representative of those encountered during flight. And thirdly, to carefully design the associated multi-instrumentation of such a test to accurately determine the damage and failure scenario with and without battery cells in such a part.